Why don't we get started? I have a bit of a time limit. I know your final's important, but my daughter has ring ceremony tonight, so my wife's coming to pick me up at 5:20. So I think that should be enough time. That's 45 minutes. But let's get started. What particular questions? So clear on the free response. You'll have this question for free response. That's number one. You will have, huh? You'll have this question, finding the electric field. You're not going to have part E, but you will have that part in the multiple choice, finding the potential. I'm just going to ask you the direction and the magnitude of the electric field, not all those individual questions. What is the magnitude? What is the direction? And it will be a situation where you have one electric field vector that's off axis, just like in this example. Second, you're going to have a question like this, resistors in series and parallel. Thirdly, you'll have a question, that's example. Like this one, where you have the charged particle going up to the wire, and you'll have the same two questions. What's the direction and the magnitude? Both of those, if you don't get both of them, it's half off of the magnetic field, and then the direction and magnitude of the force. And then finally, you're going to have, on this fourth exam, you're going to have a question like this. Now, while it's a mirror, in this case, it doesn't have to be a mirror. It can either be a mirror or a lens. Is that clear? Okay. All right, what are your particular questions? Madison? This one? Yeah. Okay, so there are variations of this question. And this one gives you the direction of the current. The other variation is where I show you the path that the particle takes, and you have to give me the direction of the current. So let's talk about both of those. Here, I have the current. It's going to the right. So I have my thumb going in the direction of the current. My fingers go into the page, under the wire, and out of the page on top of the wire. So on this side of the wire, the magnetic field is out of the page. On this side, it's into the page, but that's not important to us, right? We just want to know the region where the particle is traveling. So now I have a situation where my velocity vector is down and my magnetic field vector is out of the page. That means that the force acting on that particle is going to be to the left. So that's the force acting. So that's the answer to that question. Now, I could also say that the path of this particle is in that direction, and then I would ask you, what is the direction of the current? And you would have to first figure out what is the direction of the magnetic field that causes that motion, which would be out of the page. Okay, let's step through that actually. Let me erase everything and we will just redo that question. It's the same answer. So if I have a particle that follows that path, that means that the force is to the left, which means that my velocity vector is down, my force is in that direction. That means the magnetic field is out of the page. So the magnetic field here is out of the page. And then I ask myself the question, what direction is the current to give me that magnetic field? And it is to the right. Okay, so those are the two variations of that question. All right, Madison? All right, what else? There are 3 or 4 right-hand rule problems. When they're on the free response, you have to apply the right-hand rule on both of those. But then there are 2 or 3 or 4 maybe on the exam. 40 questions, by the way. I think I told you this. 40 multiple choice questions, 8 free response questions. Well, there are 4 questions with 2 parts each. But each of those 2 parts counts the same weight as a multiple choice. 2 hours. It's less than twice the length, but you have 2 hours. That's not it, is it? Are y'all just really ready? Yeah, Connor?
Should each draw the little letters on their fingers again?
Yeah, of course. But extra credit if you tattoo them onto your fingers. Like Guaranteed C in the class. If you know, I'm joking. Yeah,
Go
Benjamin.
through some concept questions we can see on the final.
Um, I mean, there's a bunch of those. There's probably 80 of those possible. I mean, because on each exam there's probably 15 or so on each exam, so 60. Can you narrow it down a little bit? Particular topic. Okay. So which of these is true about a mass spectrometer? So when I go through and make the exam, what I do is I pull 10 or 15 questions from each exam, and then I go through and I change them. So for example, if I had this question, it wouldn't look exactly the same. It would still probably say which of these statements is true about a mass spectrometer, but then there would be different statements about the mass spectrometer. Some of them might be the same, some of them might be similar, but probably they're all going to be different. So when you get to a question like this and you're studying for the exam, I want you to think about what all is there about the mass spectrometer that's important. And that might be where you go back to your notes or go back and look at past exams, because honestly, all my exams are the same. They're not the same, but they're all very similar. They're testing the same material. So you'll see variations of the same question. You'll see, well, what are the other things that he's asked? So that, I'm telling you to study these 4 exams, but it might be useful for you to go back and study past exams where you see questions that are similar to this. So a couple of things that you need to know about a mass spectrometer is that the magnetic force, the B force, is a centripetal force. In fact, I think, yeah, that was one of the things here that's true. It's a centripetal force, and the centripetal force is always perpendicular to the velocity. That's what that little symbol means, that upside down T, that it's always at an angle of 90 degrees. So the force is perpendicular to the velocity. As a result, that force does not change the energy. The kinetic energy, that might have been a statement here. Oh yeah, so see, number 1 here says the magnetic force increases its kinetic energy. That's not true, okay? Also, the mass spectrometer determines the mass to charge ratio, not M to G, M to Q. That's like number 14 here, where you actually have to find the mass to charge ratio. It does not determine the mass of the particle, only the mass to charge ratio. So number 2 would not be right. So the answer then would be B3 only for this. But as you're going through that, think about, well, how are the other ways that I could ask that question? The magnetic force is centripetal force. The force is perpendicular to the velocity. That's true for all centripetal forces. The force does not change the kinetic energy, and use a mass spectrometer to find the mass to charge ratio. Not the mass, not the charge, but the mass to charge ratio. Some of y'all might have used the mass spectrometer in the department. We have at least 1, maybe 2. But that's what it does. That's how it determines those particles, by measuring the mass to charge. And then we know the mass to charge ratio for certain particles, so we can, determine what that particle is. All right, we'll just sort of skim down through it. Are there particular topics that y'all want to look at? Yeah, let's go back to that. So that's been the most distant exam. So like this one, for example, number 7, where's the electric field equal to 0? That's what you're thinking, right? Where is it 0? First of all, if you have one like this, it's never going to be these, because they're all going to be off in different angles, and so they have to be along a line in order to be an electric field of 0. In general, you want to do what? Get away from what? The highest charge. You want to get away from the highest charge. And so, for example, here, knowing that general rule, I would gravitate towards C. I'm not sure that's the right answer, because it might be none of these, although that's not an option here. But I'm going to gravitate towards C. And then I can draw the electric field for each of these. Get my pen smaller. Sorry, this is a new classroom for me. Ooh, a calligraphic pen. You want some calligraphy? Or a crayon? A magic pen. Okay. So if I'm looking at C, the electric field due to positive Q is in that direction. And remember that the electric field is KQ over R squared. So what I want to know is the electric field due to this charge equal but opposite? I know it's opposite in direction because that electric field would be, in the opposite direction. It's away from that 9Q charge. So is it equal in magnitude? Notice that the charge is 9 times the amount of Q. And then also notice that while this distance is R, this distance is 3R. This is R, that's 3R. So if I have 3 here, that's 3 squared, and that 3 will cancel out with the 9 because it's squared, right? 3 doesn't cancel out with 9, but 3 squared does. So those electric fields would be equal and opposite, and C would be the right answer. Okay? So, another good way, like if you practice this question, you could see this in a variety of ways. I could give you different charges. I could give it to you just a simple on a line. You've seen previous examples like that in other exams. So you could see something similar to that as well. All right, let's just sort of skim down through here. Y'all let me know if you see anything that you want to look at. Go to the first one. Have y'all not studied much yet? Yeah, I'm sorry. I know Friday is the better day for this help session, but probably most of your studying is going to happen over the weekend. Anything in particular here, y'all? Yeah, Kylie?
Can you go over either like 4 or 5 from exam 2?
Yeah, 4 or 5 from exam 2. Okay, yeah, definitely going to see circuits. Okay, there are probably, between the capacitors and the resistors in series and parallel, there are probably 8 questions having to do with 6 to 8 questions between those. So it's a big chunk of the exam, but it's a big chunk of the semester too. And I really like these where there are a couple of these actually where I give you a voltage of something embedded in the circuit and ask you what is the voltage of other things. So we'll do both 4 and 5. So look at this. What I know is that I have 8 volts on C1. And so I can begin to step out and figure out what are some of the other voltages. If I have 8 volts across C1, what's my voltage across C2? Also 8 volts, only because those 2 capacitors are identical. If they're identical, they share the same voltage. If they're different, they do not. Okay, but if they're identical, they do. That means that I have a total of 16 volts on this top branch, which means that I have also 16 volts here and 16 volts here because capacitors in parallel have the same voltage, right? And so I have 16, 16, and 16. So the answer would be A, 16. Here, let's look at this one. This one's a little, this is just a circuit problem, which you'll have some of those too. Probably want to find the equivalent circuit for this, unless you're just really good at circuits. Probably want to find the equivalent. I know that the 3 and the 6 together in series is equivalent to 2, right? 1 over 3 plus 1 over 6, that's equal to 2. Clear on that? Okay. All right, so I can now rewrite this. I have 12 volts, 6 microfarads, and then 3 microfarads. I'll tell you where that came from in a second. 6 microfarads and 3 microfarads, 12 volts here. That 3 microfarads came about because I have 2 and 1, 2 plus 1 equals 3, so that makes a 3 microfarad capacitor. Now it's useful if you can look at these 2 capacitors and just know what the voltages are. I know that for capacitors, big capacitors have small voltages, and small capacitors have big voltages. It's opposite for resistors, but for capacitors that's true. So my 6 microfarad will have a voltage that's 1/2 the voltage of the 3 microfarad. That means the 6 microfarad is going to have what voltage? That's right, 4 volts. I have 4 volts here and 8 volts here. I know it's 4 and 8 because they have to add up to equal to 12. And I know that they're a factor of 2 different because the capacitors are a factor of 2 different. We've done this particular combination a bunch of times. I'm pretty sure it comes up on the exam in some way or another, either on capacitors or resistors. Now I want to know the voltage on C1. Well, if I know that this is 8 volts right here, that means that this is also 8 volts. So I can stop right there. I have 8 volts on that one. I also know that this one is 4 volts. That's the same as this capacitor. It's a little bit trickier to find the voltage on the 3 and the 6, because you'd have to find the equivalent and find the charge, and we don't need to do that. Most of your circuits, by the way, if you're good at circuits, you're not really going to have much work to do. You're just going to see them in your head. But write them down. Okay, write down all the little steps and don't make any mistakes, because I don't want you to make mistakes and miss a question that you should have got right. Is that okay? All right. This one too, like this one here, if I know that that top one has 8 volts, that means that 2C, that capacitor, has what voltage? Now remember, big capacitors have small voltages. So it's going to have 4 volts, right? So the 2C is going to have 4 volts. That means that this capacitor right here will have 8 plus 4 or 12 volts. Okay? All right. What else, y'all? Particular questions? Those are good. These are all good. Yeah, Madison. Number 13 on this one. I like these too. I like questions that don't have numbers, that make you think about the circuits, and these are good for that. All right, I like rankings too. There are several rankings that come up on the exam, at least. Pretty sure there's at least 2 that are on the exam. All right, rank these from the bright to least bright. When you're talking about brightness, you're talking about power, okay? And power, I know, is V squared over R. So I want to rank them in terms of their voltage. Let's see, I know that this one has a voltage V. I know that this one over here has a voltage V over 2. So I know that D is bigger than A. That doesn't help me much. And then B and C. Well, let's give them numbers, actually. Numbers are probably easier to put numbers on this. So if I say that this is 12 volts, and this is 12 volts, and this is 12 volts, that means that I have 12 volts here. I have 6 volts on this one. And then that means that I have over here, I have a 12 volt with a resistor and another resistor. This is R, and this is, that's not easy to do, is it? I know that this resistor right here has or rather, this total circuit has a resistance that's less than this circuit. How do I know that that's true? How do I know that the resistance of the second circuit has a lower resistance than the first circuit?
Parallel reduces the resistance.
Right. So when I add 2 resistors in parallel, the resistance goes down. So because of that, erase some of this. Because of that, I know that this overall resistance is smaller than this overall resistance, so that this light bulb gets more current and voltage than this light bulb. So this one has a higher voltage and a higher current than this one does. Because this circuit has an overall larger, overall smaller resistance, this one gets more current, more voltage than this bulb does. So if I'm ranking from, when we're going from most to least bright, then that means that I can rank B as being higher than A. So let's see, that doesn't help me either. But then the voltage across B is going to be bigger than the voltage across C. Which gets rid of this one. Sorry, I'm not used to this computer. What problem was that? 13. B is bigger than C, so that means that it should be D, B, C, and A. That if I know that this bulb has a bigger voltage than this, yeah,
Well, the answer key says A.
DBAC. I don't remember. Yeah, no, it is A. You're right. Oh gosh, how do we think about this? So, yeah,
Is it because the resistance on C is lower because it's in parallel?
the resistance is lower on C.
And then the voltage goes to the one with higher resistance.
Mhm.
Lower resistance.
Yeah, so this one has a low voltage. This one has the highest. This one has a higher voltage than C. So B would be bigger than C. And then has a higher voltage than B. A has a smaller voltage than B. I forget how I did that. I think maybe I put numbers in it. Did I do numbers in it? Was that the way we looked at it? I don't remember what those numbers were, because it doesn't work out very easily. Don't take my unfamiliarity with this problem, because it's been a while since I worked it. Don't take it as a note that you're not going to see a problem very similar to this, because you will see several problems with light bulbs like this. Okay? Is that clear? Kinda clear?
Put the two in the, like the middle ones together, the two light bulbs, is it 1/2 C or would it be 2 C?
When I put the two
Like
light
you're combining
bulbs,
those two in parallel.
the two in the middle, no, it's more complicated than that, because the equivalent resistance is the 1 over R plus 1 over R. So
That
that,
was a small middle.
what is that? 1 over R plus 1 over R. And that's 1 over 2. Oh, yeah, so that's R over 2. Yeah, 1/2 R. So this would be R over 2. Both of these would have the same voltage. This is R and R. Now look back at the video on that, okay? Don't take my faulting explanation. It's been a while. Still got ring ceremony in my head, okay? But look back, because you will see some light bulb questions. There's at least 2 on the exam. I think there was another one on this exam. Is that right? Yeah, see, there's another one. Okay? Is that clear? Not an unimportant question. Go back and review it. I forget who asked. Madison, did you ask about that? Okay. Is that clear what I'm saying? All right. Okay. What else, y'all? Yeah, Gabby? Yeah, of course. Yeah, so number 11, you're calculating the resistivity. So I know that R is equal to rho L over A. And in order to find the resistivity, or I want to find the resistivity, and then I can select it from these materials. So I know that rho is equal to RA divided by L. Okay? So I need to first find, I know the current, I know the area, and I know the voltage. So I'm missing then the resistance. So the first thing I need to do is find the resistance. I know that R is equal to V over I. That's from Ohm's law. That's 1.4 over 20. That's what, 0.7 ohms? That's right, isn't it? Yeah, 0.7 ohms. And now I can put in the values here. I have 0.7 is the resistance. The current is 20 divided by the area, which is 7.85 times 10 to the minus 7. And then that gives me the value for the resistivity. What was the answer for this one? You might know. D? Okay, so it's tungsten. That means when you did this, you would have found that this is equal to 5.5 times 10 to the minus 8. And then that's tungsten, D. Select it from there. So that one's more straightforward, that you're just calculating a number. Okay. What?
For number 18, well, this is gonna be like a simple one like that, or if there's a question like that, it's simple like that.
It'll be simple like that. Okay. It is a little bit more complicated. It is a two-step thing, but it's not like the ones in the past that I've given. Is that clear? Right, now that Ben's gone, I can tell you all the answers. Is that okay? Yeah, hear me. Okay. Any other questions? Or other questions? Madison? On this one? Okay, yeah. An important question is not on the free response, so you can bet that I'm going to put it in the multiple choice. So you'll see both of these. So first you want to know which of the equations is correct. The way that you do that is you just go one by one. The first one is 14 minus 4i1. I always go in order and I always start. So I'm going to start right here. And I know I'm going in this order because I have 14 and then I have this 4i1. So 14 minus 4i1 going around, following my rules. Do y'all remember the rules? No? Okay, so if I'm going through a resistor, if I'm going with the current, the change in potential is equal to minus IR. That's if I'm going with the current. So if the current's in this direction, I'm going with the current. If I'm going opposite the current, then it's the opposite. Delta V is equal to plus IR. For batteries, if I'm going in this direction, my traveling direction, doesn't matter about the current. The current is unimportant. That has a positive change in potential. And if I'm going the opposite direction, that is from big to little, high to low, then that is a negative change in potential. Go back and review those rules because they are important for this question in order to know the correct equations. So let me erase this. We'll step back through that. So with that in mind, as I'm looking at this equation, which turns out to be the right answer, I'm starting here. I should have a positive 14 because I'm going from little to big. That's like right here. I should have a negative 4i1 because I'm going with the current. That's like right here. And then coming back down here, I have a plus 6 right here. That's like this situation where I'm going from little to big, and then I come back to where I started. So A is the right answer, okay? But let's look at some of the wrong ones. The junction rule should be, well, I just pick any junction. I1 and I2 are coming in. I3 is going out. So it should be I1 plus I2 equals I3. That's not what it says. So that one's not right. And then 10 plus 6i2 plus 6, that is starting here and going in that direction. 10 is correct. That's going from little to big, so it should be a positive voltage. Plus 6i2, that's like this. I'm going opposite the direction of the current. Notice the current's going to the left, but I'm traveling to the right. So okay so far. But then as I come down here to this battery, the plus 6, that should not be plus 6. It should be minus 6. Okay, it should be minus 6 right there because that would be like this scenario. So that one's not right. And then 14 plus 4i1 14, it shouldn't be plus 4i1, it should be minus 4i1. And then plus 10 is correct, plus 6i2 is correct, but it should be minus right there. So A is the right answer. Then, I want to know what is the current through the 4 ohm resistor. Usually, the correct equation, if you get that right, usually you can use that equation to find that current. So if you've done the first one right, then the second one is easy because now I know the equation to find that current. It's 14 minus 4i1 plus 6 is equal to 0, and I solve that for I1. That's 20. It should be 5 amps. Okay? Doesn't necessarily have to be the case that the equation from the first problem carries over into the second one, but often it does. I'm not sure if it does on your exam. But I am sure that you will see two multi-loop circuits, for sure, okay? Because it's not on your free response. In general, that's true. If something's not on your free response, I tend to have more of it. And if something is on your free response, I tend to have less of it. Okay? What else, y'all? Is that it? Okay. I will have limited availability over the weekend. I'm going to Ruston tomorrow to see my son. He's playing in an ensemble. But I will have availability over the weekend. And then, of course, on Monday morning, I'll be around. Our exam's not till 1 o'clock. So if y'all want to come by and see me or chat, or you just have questions, or you just need some, refresher or whatever on various topics, then I'll be around. Appreciate y'all coming.